Imagine our sun, not as the steady, unchanging beacon we see each day, but as a living, breathing star with moods as complex and varied as an ocean during a storm. While it appears constant from our distant vantage point on Earth, our nearest star is actually a churning cauldron of magnetic fields and superheated plasma, occasionally erupting with forces so powerful they can reach across 93 million miles of space to gently brush our planet with invisible fingers of charged particles and magnetic energy. The sun's surface, though we call it a surface, is actually more like the visible top of a vast atmospheric ocean. Beneath what we can see lies a nuclear furnace where hydrogen atoms fuse into helium at temperatures of millions of degrees, creating the steady stream of light and heat that makes life on Earth possible. But it's the sun's magnetic field, invisible, ever-changing, and incredibly complex, that creates the cosmic weather that occasionally reaches out to touch our world. Picture the sun's magnetic field lines like invisible rubber bands, stretched and twisted by the constant rotation of our star. The sun doesn't rotate as a solid body like Earth does. Instead, its equator spins faster than its poles, creating a differential rotation that gradually winds up these magnetic field lines like a cosmic clock spring being wound tighter and tighter. Eventually, the tension becomes too great, and the magnetic field lines snap and reconnect in spectacular displays of energy that would dwarf all the power humanity has ever generated. These magnetic reconnection events create what scientists call solar flares, sudden releases of electromagnetic energy that can be millions of times more powerful than all the nuclear weapons ever built, yet happening in a space smaller than Earth's diameter. When viewed through specialized telescopes that can see the sun's magnetic fields, these flares appear as brilliant arcs of plasma following the magnetic field lines, creating structures that look like enormous loops and bridges connecting different regions of the solar surface. But solar flares are just one type of solar storm. Even more dramatic are coronal mass ejections, or CMEs, which occur when the sun literally hurls part of itself into space. Imagine a bubble of magnetized plasma, a cloud of charged particles bound together by magnetic fields, being expelled from the sun's outer atmosphere at speeds that can exceed 1,000,000 miles per hour. These bubbles can contain billions of tons of solar material and carry magnetic fields with them as they race across the solar system. The journey from sun to Earth takes these cosmic storms between 1 and 5 days, depending on their speed and the route they take through the solar wind. That constant, gentle stream of particles that flows outward from our star in all directions. During this journey, the storm cloud expands and evolves, sometimes growing to sizes larger than the distance between Earth and Moon, becoming a traveling disturbance in the fabric of space itself. What makes these solar storms particularly fascinating is their cyclical nature. The sun follows an 11-year cycle of activity, oscillating between periods of relative calm and periods of intense magnetic activity. During solar minimum, the sun's surface appears relatively quiet, with few sunspots and minimal storm activity. But as the cycle progresses towards solar maximum, the sun's magnetic field becomes increasingly tangled and complex, leading to more frequent and more powerful eruptions. Sunspots themselves are windows into the sun's magnetic soul. These dark patches on the solar surface, some larger than Earth, appear dark only because they're cooler than their surroundings. though cooler still means temperatures of around 6,000 degrees Fahrenheit. They form where powerful magnetic fields break through the sun's surface, creating regions where the normal convection of hot plasma is suppressed. These magnetic field bundles are like coiled springs of energy, storing power that can be suddenly released in flares and CMEs. The complexity of the sun's magnetic field creates patterns that change over timescales from minutes to decades. Solar astronomers have learned to read these patterns like weather forecasters read atmospheric pressure maps, identifying regions where the magnetic stress is building and storms are likely to occur. Advanced computer models now attempt to predict space weather, though the sun's chaotic nature makes this as challenging as predicting terrestrial weather, if not more so. What emerges from studying solar storms is an appreciation for the delicate balance that exists between our star and our planet. The sun's magnetic field and the solar wind it drives actually help protect us from cosmic radiation coming from outside our solar system, creating a magnetic bubble called the heliosphere that deflects harmful galactic cosmic rays. Yet this same system can occasionally direct powerful storms toward Earth, creating both challenges and spectacular beauty when these cosmic forces interact with our planet's own magnetic field. The Earth orbits through this dynamic, ever-changing environment of solar plasma and magnetic fields, riding the solar system's cosmic weather like a ship navigating an invisible ocean. Most of the time, this journey is smooth and uneventful, with Earth's magnetic field deflecting the solar wind around our planet like water flowing around a stone in a stream. But when solar storms arrive, bringing with them enhanced magnetic fields and increased particle densities, the normally gentle interaction between solar wind and terrestrial magnetism transforms into something far more dramatic and beautiful. In the quiet moments between solar storms, space near Earth is filled with a subtle dance of magnetic fields and particle flows, creating the conditions that make possible some of nature's most magnificent displays. The auroras that paint the polar skies in curtains of green, blue, and red light, visible reminders of the cosmic weather that surrounds our world. Earth's magnetic shield and aurora magic, when sky meets space. High above your head, even as you rest peacefully in the quiet darkness of night, an invisible battle of cosmic proportions plays out in silence. Earth's magnetic field, our planet's ancient shield against the solar wind, stretches tens of thousands of miles into space, creating a protective bubble around our world that deflects most of the charged particles streaming constantly from our sun. This magnetosphere, as scientists call it, is one of the reasons life has been able to flourish on Earth for billions of years. Yet most of us live our entire lives without ever seeing direct evidence of its existence. Until, that is, a solar storm arrives and the sky begins to dance. Picture Earth's magnetic field as an enormous, invisible teardrop surrounding our planet. The field lines emerge from near the South Pole, arc high into space, and converge again near the North Pole, creating a protective cocoon that extends far beyond the Moon's orbit on the day side and stretches into a long tail on the night side, like a cosmic windsock showing the direction of the solar wind. This field is generated deep within Earth's core, where the motion of liquid iron creates creates electrical currents that, in turn, produce the magnetic field that has protected our atmosphere for over 3 billion years. When the solar wind, that constant, gentle stream of charged particles from the sun, encounters Earth's magnetosphere, something beautiful happens. The solar wind, traveling at speeds of several hundred miles per second, meets an immovable object in our magnetic field. Most of the time, this interaction is like water flowing smoothly around a stone in a stream. The solar wind splits and flows around Earth's magnetic field, creating a bow shockwave far upstream of our planet, similar to the wake that forms in front of a boat moving through water. But when a solar storm arrives, a coronal mass ejection or enhanced solar wind, carrying stronger magnetic fields, this gentle interaction transforms into something far more dramatic. The additional particles and energy compress Earth's magnetosphere, sometimes pushing it so close to our planet that the outer edge of our magnetic shield drops from its usual position at about 40,000 miles above Earth to less than half that distance. Satellites in high orbit can suddenly find themselves outside the protection of Earth's magnetic field, exposed to the full force of the cosmic storm. As the storm-enhanced solar wind presses against our magnetosphere, energy builds up in Earth's magnetic tail like water behind a dam. The magnetic field lines on the night side of Earth stretch and distort, storing enormous amounts of energy in their invisible structure. Eventually, this energy must be released, and when it is, the results are spectacular. Magnetic field lines suddenly snap back toward Earth like cosmic rubber bands, accelerating charged particles down toward our planet's polar regions at tremendous speeds. These accelerated particles, mostly electrons and protons from the solar wind, race along Earth's magnetic field lines toward the magnetic poles, where the field lines converge and point directly down into our atmosphere. As they descend, they encounter something that transforms their invisible energy into one of nature's most magnificent displays, our atmosphere itself. At altitudes between 60 and 400 miles above Earth's surface, these high-energy particles begin colliding with atoms and molecules in our increasingly dense atmosphere. Each collision transfers energy from the speeding particles to atmospheric gases, causing them to emit light, the same basic process that makes a neon sign glow, but painted across the sky on a scale that dwarfs anything humans have ever created. The colors of the aurora tell the story of these cosmic collisions with poetic precision. When the charged particles strike oxygen atoms at high altitudes, around 200 to 300 miles up, they produce that ethereal red glow that occasionally caps the most spectacular auroral displays. Lower down, at altitudes around 60 to 150 miles, oxygen produces the familiar green light that dominates most auroras, creating those flowing curtains of emerald radiance that seem to dance across the polar skies. Nitrogen molecules create their own contributions to this celestial light show. When struck by the incoming particles, nitrogen can produce blue and purple hues, adding depth and complexity to the auroral palette. The interplay of these different gases at different altitudes creates auroras that can shift from green to red to blue in moments, as changing conditions in space alter the energy and composition of the particle stream flowing down Earth's magnetic field lines. The shapes and movements of auroras reflect the invisible architecture of Earth's magnetic field made suddenly visible. Those graceful arcs that stretch across the sky follow the curvature of magnetic field lines. The rippling, dancing motion of auroral curtains mirrors the turbulence in the magnetosphere high above, where magnetic fields twisted by solar storms create eddies and flows in the stream of particles descending toward Earth. During the most intense geomagnetic storms, when particularly powerful solar eruptions send massive clouds of magnetized plasma toward Earth, the aurora can intensify beyond anything normally seen. The usual oval of auroral activity around each magnetic pole can expand dramatically, bringing the northern lights as far south as the Caribbean and making the southern aurora visible from Tasmania. These rare events transform the night sky into a living cathedral of light, with pillars of radiance stretching from horizon to zenith and colors so intense they can be seen even through city lights. But auroras are more than just beautiful. They're visible indicators of the cosmic weather affecting our entire planet. The same storms that create spectacular auroral displays can also disrupt radio communications, interfere with GPS navigation, and even cause power grids to fail. The charged particles that paint the sky with light also pose risks to astronauts and airline crews flying polar routes, where Earth's magnetic field provides less protection from cosmic radiation. Indigenous peoples of the Arctic have watched auroras for thousands of years, developing rich mythologies to explain these dancing lights. The Inuit spoke of spirits playing ball with a walrus skull across the sky. Norse cultures saw the aurora as light reflecting off the shields of the Valkyries as they escorted fallen warriors to Valhalla. Finnish folklore described the aurora as caused by the firefox running so fast across the snow that its tail swept up snowflakes that sparkled in the moonlight. Modern science has revealed the true mechanism behind these lights, but the sense of wonder remains unchanged. Each aurora is a visible reminder that Earth exists within the Sun's extended atmosphere, that we ride through space surrounded by invisible fields and forces that occasionally reveal themselves in displays of ethereal beauty. The dancing lights in polar skies connect us directly to our nearest star, making visible the cosmic weather that flows constantly between Sun and Earth, usually hidden but always present, like a secret conversation between celestial bodies, written in languages of magnetism and light. The invisible web, how space weather touches our daily lives. In the gentle quiet of your evening routine, as you check your phone one last time before sleep, send a final text message, or set your alarm for tomorrow, you're participating in an intricate technological dance that extends far beyond Earth's atmosphere. The invisible web of satellites, radio waves, and electromagnetic signals that makes modern life possible exists in constant dialogue with the cosmic weather flowing from our Sun, creating connections between solar storms and the most mundane moments of our daily existence. Consider the remarkable journey of a simple GPS signal that helps you navigate to an unfamiliar destination. High above Earth, a constellation of satellites orbits at an altitude of about 12,000 miles, each one carrying atomic clocks so precise they measure time to billionths of a second. These satellites continuously broadcast timing signals that travel at the speed of light through the ionosphere, that electrically charged layer of our upper atmosphere that extends from about 50 to 400 miles above Earth's surface. Under normal conditions, this system works with extraordinary precision, allowing your phone to determine your location within a few meters by comparing the timing of signals from multiple satellites. But the ionosphere is not a static layer. It's a dynamic, ever-changing region that responds to solar radiation and space weather like a vast atmospheric mood ring, constantly shifting its density and electrical properties in response to conditions in space. During quiet solar periods, the ionosphere maintains relatively stable layers of charged particles, created by solar ultraviolet radiation gently ionizing atoms and molecules in the upper atmosphere. Radio waves and satellite signals can predict their path through these layers with reasonable accuracy. But when a solar storm arrives, carrying enhanced radiation and charged particles, the ionosphere becomes turbulent and unpredictable, like a clear mountain stream suddenly becoming a rushing torrent filled with debris. The charged particles from solar storms can dramatically increase the density of electrons in the ionosphere, creating regions of enhanced electrical activity that bend, reflect, or absorb radio signals in unexpected ways. Your GPS might suddenly think you're several miles from your actual location or lose signal entirely. Amateur radio operators, who have long served as informal sentinels of space weather, find that normally reliable communication paths across continents suddenly vanish, while other frequencies that usually can't travel beyond the horizon suddenly bounce around the world with crystal clarity. Airlines face more subtle but equally important challenges from space weather. The same charged particles that create beautiful auroras also increase radiation levels in Earth's upper atmosphere, particularly near the polar regions, where Earth's magnetic field provides less protection. During major solar storms, radiation levels at typical airline cruising altitudes can increase by factors of 10 or more, especially on polar routes that connect North America to Asia across the Arctic. While this enhanced radiation poses little risk to passengers on occasional flights, it can be significant for flight crews who spend hundreds of hours per year at high altitudes. During severe space weather events, airlines sometimes reroute flights to lower altitudes or more southern paths, adding time and fuel costs to avoid exposing crews and passengers to elevated radiation levels. The invisible cosmic weather that creates stunning auroras thus quietly influences flight schedules and travel times around the globe. Perhaps even more dramatically, intense solar storms can affect power grids with a phenomenon that seems almost magical in its mechanism. When a coronal mass ejection arrives at Earth and compresses our magnetosphere, it doesn't just create auroras. It also induces electrical currents in any large conductor, including the extensive networks of power lines that carry electricity across continents. These geomagnetically induced currents can flow through power grids like uninvited electrical guests, causing transformers to overheat and protective systems to shut down. The most famous example occurred in March 1989, when a powerful geomagnetic storm caused the entire Quebec power grid to fail, leaving 6 million people without electricity for 9 hours. The storm induced currents that tripped protective relays and damaged transformers, creating a cascading failure that spread across the province in less than 2 minutes. Similar events have affected power systems from Sweden to South Africa, demonstrating that cosmic weather recognizes no national boundaries. Satellites, those silent servants that enable everything from television broadcasts to weather forecasting, face their own unique challenges from space weather. During solar storms, the increased density of Earth's upper atmosphere creates additional drag on low-orbiting satellites, causing them to lose altitude more quickly and requiring more frequent orbit corrections. The charged particle environment can also build up static electricity on satellite surfaces, occasionally leading to electrical discharges that can damage sensitive electronic components. Even more subtly, space weather affects the countless radio signals that carry our communications around the world. High-frequency radio waves, used for everything from international broadcasting to emergency communications, depend on the ionosphere to reflect them back to Earth, enabling communication far beyond the line of sight. During geomagnetic disturbances, these reflecting layers can become turbulent or disappear entirely, creating radio blackouts that can last for hours or even days. The internet itself, though it might seem immune to cosmic influences, can be affected when space weather disrupts the satellite links and radio systems that connect remote regions to the global network. Undersea cables that carry much of the world's internet traffic can also experience induced currents during major geomagnetic storms, though their shielding and redundancy usually prevent significant disruptions. What makes space weather particularly challenging for our technological civilization is its unpredictability and global reach. A solar storm that begins with a magnetic explosion on the Sun can affect systems across the entire daylit hemisphere of Earth simultaneously, creating coordinated disruptions that can cascade through interconnected technological systems in unexpected ways. A GPS disruption might affect precision agriculture, while a radio blackout could interfere with air traffic control, demonstrating the invisible threads that connect space weather to virtually every aspect of modern life. Yet for all these potential disruptions, it's worth remembering that space weather also enables some of the very technologies it occasionally disrupts. The ionosphere that can bend GPS signals during storms is the same layer that makes long-distance radio communication possible during quiet periods. The solar radiation that can interfere with satellites is also what powers many spacecraft through their solar panels and creates the upper atmospheric conditions necessary for certain types of scientific research. As our civilization becomes increasingly dependent on space-based technology, we've developed a growing appreciation for the need to monitor and predict space weather. Networks of ground-based magnetometers measure Earth's magnetic field variations, while satellites positioned between Earth and Sun provide early warning of approaching solar storms. This space weather monitoring system operates continuously, like a cosmic early warning network, helping power companies, airlines, and satellite operators prepare for the invisible storms that periodically sweep through our solar system. In the gentle rhythm of our daily lives, space weather usually remains invisible and unfelt, a cosmic backdrop to our earthbound concerns. But occasionally, when the Sun's magnetic field unleashes its stored energy and sends powerful storms racing across the void toward Earth, we're reminded that our technological civilization exists not in isolation, but as part of a vast, interconnected system that stretches from our planet's core to our nearest star, united by invisible forces that occasionally reveal themselves in both beautiful and disruptive ways. The Great Magnetic Umbrella, Earth's ancient shield against the cosmos. Deep beneath your feet, nearly 2,000 miles down in Earth's liquid outer core, currents of molten iron flow in vast, slow-moving rivers that have been circulating for billions of years. These currents, driven by the planet's rotation and the heat from Earth's solid inner core, create electrical fields that generate something remarkable, a magnetic field so large it extends far into space, creating an invisible protective bubble around our entire planet. This magnetosphere is perhaps Earth's most underappreciated feature, a cosmic umbrella that has quietly protected life on our planet since complex organisms first began to evolve. To truly appreciate the magnetosphere's role in cosmic weather, imagine Earth without it. Mars offers us a sobering example of what our planet might look like if this magnetic shield had failed. Billions of years ago, Mars likely had a substantial atmosphere, possibly thick enough to support liquid water on its surface. But without a strong magnetic field to deflect the solar wind, Mars's atmosphere was gradually stripped away particle by particle over millions of years. Today, the red planet's atmosphere is less than 1% as dense as Earth's, and its surface is bombarded by radiation that would be lethal to most Earth life. Earth's magnetosphere extends roughly 40,000 miles toward the Sun and stretches behind our planet in a long tail that reaches well beyond the Moon's orbit. This invisible structure is constantly being sculpted by the solar wind, like a flag streaming in a cosmic breeze. During quiet solar periods, the magnetosphere maintains a relatively stable teardrop shape, with a rounded front face that deflects the solar wind, and a long tail that extends away from the Sun like a cosmic windsock. But cosmic weather brings much more than just the steady solar wind. Our solar system is filled with various forms of space weather, each interacting with Earth's magnetic shield in different ways. High-energy cosmic rays, originating from distant stellar explosions and accelerated to nearly the speed of light, constantly bombard our solar system from all directions. These cosmic rays carry so much energy that they can penetrate deep into planetary atmospheres and even reach the surface of worlds without magnetic protection. Earth's magnetosphere deflects most of these cosmic rays, bending their paths as they approach our planet and sending them harmlessly around us. The few that do penetrate our magnetic shield are mostly channeled toward the polar regions, where they contribute to the particle bombardment that creates auroras. Without this magnetic deflection, cosmic ray bombardment at Earth's surface would be many times higher, potentially making the evolution of complex life far more difficult or impossible. The interaction between different types of cosmic weather and Earth's magnetosphere creates a constantly changing environment in near-Earth space. During periods of low solar activity, when the solar wind is weak and steady, the magnetosphere expands outward, providing maximum protection for our planet. The boundary between Earth's magnetic field and interplanetary space, called the magnetopause, sits comfortably far from Earth, and the radiation environment in near-Earth space remains relatively benign. But when solar storms arrive, the entire system transforms dramatically. A coronal mass ejection approaching Earth is like a massive magnetic bulldozer pushing through space. When it collides with Earth's magnetosphere, it can compress our magnetic field to half its normal size, bringing the outer boundary of our protective shield much closer to Earth. Satellites that normally orbit safely within the magnetosphere can suddenly find themselves outside its protection, exposed to the full fury of the cosmic storm. The compression of the magnetosphere during major storms also changes the shape and behavior of the radiation belts. Those donut-shaped regions around Earth where high-energy particles are trapped by our magnetic field. Discovered in the 1950s by physicist James Van Allen, these radiation belts normally exist in two stable bands, one extending from about 400 to 4,000 miles above Earth, and another from about 8,000 to 40,000 miles up. During geomagnetic storms, these radiation belts can become highly dynamic and unpredictable. New belts can form temporarily, existing belts can merge or split apart, and the population of energetic particles can increase by orders of magnitude. These changes create hazardous radiation environments for spacecraft and can affect satellites in ways that persist long after the original storm has passed. The magnetosphere's tail region, stretching away from Earth on the night side of our planet, becomes particularly active during cosmic weather events. As solar storms compress the front of the magnetosphere, energy builds up in the magnetic tail like water behind a dam. Eventually, this stored energy is released in what scientists call substorms, sudden reconfigurations of the magnetic field that accelerate particles earthward, creating the enhanced auroral displays that mark major geomagnetic events. These substorms can occur multiple times during a single geomagnetic storm, each one sending pulses of energetic particles down Earth's magnetic field lines toward the polar regions. The result is a dynamic, ever-changing light show in the polar skies, as different substorms create different patterns and intensities of auroral activity throughout the night. One of the most fascinating aspects of Earth's magnetic shield is how it has evolved over geological time. The magnetic field is not constant. It weakens and strengthens over thousands of years, and occasionally it even reverses completely, with magnetic north and south poles switching positions. These magnetic reversals happen every few 100,000 years on average, and during the transition period, which can last several thousand years, Earth's magnetic protection is significantly weakened. The most recent reversal occurred about 780,000 years ago, and some scientists believe we may be entering another reversal period now, as Earth's magnetic field has been weakening steadily over the past few centuries. During a magnetic reversal, our planet would be much more vulnerable to cosmic weather, potentially experiencing enhanced radiation levels and more frequent disruptions to technology that depends on stable magnetic conditions. Yet, even during normal periods, the magnetosphere is a dynamic, ever-changing system. It breathes with the solar wind, expanding and contracting as solar conditions change. It develops waves and oscillations that propagate through the magnetic field like ripples on a cosmic pond. It creates its own weather patterns in the form of magnetic storms and substorms that redistribute energy and particles throughout near-Earth space. The magnetosphere also interacts with Earth's upper atmosphere in complex ways. During major geomagnetic storms, energy deposited in the polar regions can heat the upper atmosphere, causing it to expand and increase drag on low-orbiting satellites. This coupling between space weather and atmospheric weather creates feedback loops that can amplify or dampen the effects of cosmic storms. Perhaps most remarkably, Earth's magnetosphere may have played a crucial role in the development of life on our planet, by protecting our atmosphere from being stripped away by the solar wind and by shielding the surface from harmful cosmic radiation. The magnetosphere created stable conditions that allowed life to evolve and flourish over billions of years. As we drift towards sleep, surrounded by the gentle protection of Earth's magnetic embrace, we can appreciate that this invisible shield continues its ancient vigil, deflecting cosmic storms and channeling the universe's high-energy particles safely around our world, ensuring that tomorrow's sunrise will illuminate a planet still blessed with the atmospheric blanket and protective magnetic field that make our existence possible. Galactic winds and stellar storms, weather beyond our solar system. While we've explored the intimate dance between Earth and our Sun, cosmic weather extends far beyond the boundaries of our solar system, encompassing forces and phenomena that operate on scales almost too vast to comprehend. Our entire solar system is itself a small vessel sailing through an ocean of galactic weather. Streams of cosmic rays, interstellar winds, and the influence of distant stellar explosions that have been shaping conditions in our corner of the galaxy for billions of years. Imagine our solar system as a bubble of influence, created by our Sun's magnetic field and solar wind, called the heliosphere. This vast magnetic bubble extends far beyond the orbit of Pluto, reaching perhaps 100 times the distance from Earth to the Sun before it finally encounters the interstellar medium, the thin gas and dust that fills the space between stars. At this boundary, called the heliopause, our Sun's influence ends and true interstellar space begins, marking the edge of our cosmic neighborhood. The journey to this boundary takes the solar wind decades to complete, gradually slowing as it pushes against the resistance of interstellar space. When NASA's Voyager 1 spacecraft crossed this boundary in 2012, after a 35-year journey, it discovered that interstellar space is not the empty void we once imagined. Instead, it's filled with its own weather systems, streams of charged particles, magnetic fields, and the remnants of ancient stellar explosions that create a complex, dynamic environment extending across the galaxy. The most energetic component of this galactic weather consists of cosmic rays, subatomic particles accelerated to incredible speeds by some of the most violent events in the universe. Unlike the relatively gentle particles of the solar wind, cosmic rays carry energies millions of times greater, having been accelerated by supernova explosions, colliding neutron stars, and the supermassive black holes that lurk at the centers of galaxies. These particles race through space at nearly the speed of light, carrying enough energy to penetrate deep into planetary atmospheres and even reach the surface of unprotected worlds. Our Sun's magnetic field and solar wind provide some protection from galactic cosmic rays, creating a partially effective shield around our solar system. During periods of high solar activity, when the solar wind is strongest, fewer galactic cosmic rays can penetrate into the inner solar system. Conversely, during solar minimum periods, when our star's activity is low, more of these high-energy particles from deep space can reach the inner planets, including Earth. This creates an interesting paradox in cosmic weather. Sometimes we're better protected from galactic radiation when our own star is more active and potentially disruptive. It's as if living near an active volcano provides some protection from distant earthquakes, even while creating its own periodic hazards. This delicate balance between solar and galactic influences has likely shaped the evolution of life on Earth in subtle but important ways over geological timescales. The interstellar medium through which our solar system travels is far from uniform. Our Sun and its family of planets are currently passing through a region of space called the local interstellar cloud, a relatively warm and thin region of gas and dust that extends for several light years around us. This cosmic cloud is itself moving through space, part of a larger structure called the local bubble, a cavity in the interstellar medium likely created by ancient supernova explosions that swept the region clear of denser material millions of years ago. As our solar system orbits the center of the Milky Way galaxy, completing one full orbit every 225 million years, it encounters different regions of interstellar space with varying densities of gas, dust, and magnetic fields. Sometimes we pass through denser regions where the pressure on our heliosphere increases, potentially compressing our Sun's protective bubble and allowing more galactic cosmic rays to penetrate toward Earth. At other times, we travel through more rarefied regions, where our solar system can expand its influence farther into space. These galactic scale changes occur over timescales so long that they're essentially imperceptible to human civilization. Yet, they may have profound effects on planetary climates and the evolution of life. Some scientists have proposed that our solar system's passage through dense interstellar clouds might trigger ice ages on Earth by increasing cosmic ray bombardment of our atmosphere, which could enhance cloud formation and cooling. While this remains a subject of active research and debate, it illustrates how cosmic weather operates on multiple scales, from the immediate effects of solar storms to the vast, slow-moving influences of galactic structure. The stars themselves contribute to galactic weather through their stellar winds and occasional explosive deaths. Every star in our galaxy produces its own version of the solar wind, and massive stars can create stellar winds thousands of times more powerful than our suns. When these stars eventually explode as supernovas, they release as much energy in a few seconds as our sun will produce over its entire 10 billion year lifetime, sending shock waves rippling through interstellar space at speeds of thousands of miles per second. These supernova shock waves can travel for hundreds of thousands of years, sweeping up interstellar gas and dust, accelerating particles to cosmic ray energies, and creating the hot, low-density bubbles in the interstellar medium that our solar system currently inhabits. The local bubble that surrounds us was likely created by a series of supernova explosions that occurred relatively nearby in astronomical terms, within a few hundred light-years of our current position, sometime between 10 and 20 million years ago. Even more exotic forms of galactic weather emerge from the most extreme objects in our galaxy. Neutron stars, the incredibly dense remnants of massive stars that have collapsed to city-sized objects containing more mass than our sun, can generate magnetic fields trillions of times stronger than Earth's. When these objects spin rapidly, they create lighthouse-like beams of radiation that sweep across space, and occasionally they can produce sudden bursts of energy that temporarily outshine entire galaxies. Black holes, particularly the supermassive black hole at the center of our galaxy, create their own forms of cosmic weather. As material spirals into these gravitational monsters, it heats up and produces powerful jets of particles and radiation that extend for thousands of light years into space. These jets can influence star formation across vast regions of the galaxy and contribute to the population of high-energy cosmic rays that eventually reach our solar system. Perhaps most intriguingly, our galaxy itself moves through a larger cosmic environment, interacting with other galaxies in our local group and feeling the gravitational influences of even more distant galactic clusters. The Milky Way is currently on a collision course with our nearest large galactic neighbor, Andromeda, though this cosmic traffic accident won't occur for another 4.5 billion years. Long before that event, gravitational interactions between the galaxies may alter the orbits of stars and solar systems throughout both galaxies, potentially changing the galactic weather patterns that have persisted for millions of years. The study of galactic weather is still in its infancy, limited by the vast scales involved and the long timescales over which these processes operate. Unlike solar weather, which we can observe changing over hours and days, galactic weather patterns evolve over millions or billions of years, making them difficult to study directly. Yet as our understanding grows, we're beginning to appreciate that Earth's environment is influenced not just by our sun, but by the entire galaxy that contains us. In the gentle stillness of a clear night, when you look up at the stars scattered across the sky, you're seeing the local neighborhood of our galactic weather system. Those distant points of light are the sources and shapers of cosmic rays, stellar winds, and interstellar magnetic fields that have been influencing our solar system since long before Earth formed. The cosmic weather that surrounds us connects our small planet to the grandest scales of the universe, making us participants in weather systems that span not just our solar system, but our entire galaxy and beyond. Watching the invisible sky, the art and science of space weather forecasting. In quiet rooms filled with softly glowing monitors, scientists around the world maintain a constant vigil over conditions in space, watching for the subtle signs that herald the approach of cosmic storms. This is the gentle art of space weather forecasting, a discipline that combines the precision of physics with the intuition of meteorology, seeking patterns in the invisible forces that flow between Earth and Sun. The challenge of predicting space weather begins with understanding a star that operates by rules very different from terrestrial weather systems. The Sun's behavior emerges from the complex interaction of nuclear fusion, magnetic fields, and plasma dynamics operating under conditions that exist nowhere else in our solar system. Predicting when this magnificent chaos will produce storms that affect Earth requires a network of observers both on our planet and in space, working together to create an early warning system for cosmic weather. The foundation of space weather monitoring rests on a global network of magnetometers, sensitive instruments scattered across continents from Alaska to Antarctica that can detect the subtle changes in Earth's magnetic field, heralding the arrival of solar storms. When a coronal mass ejection compresses Earth's magnetosphere, these devices register the change almost simultaneously, providing forecasters with real-time information about conditions in near-Earth space. But ground-based monitoring can only tell us what's already happening at Earth. To provide advance warning, scientists have positioned spacecraft at the L1 Lagrange point, a gravitationally stable location about 1 million miles from Earth toward the Sun. These cosmic weather stations measure the speed, density, and magnetic field orientation of the solar wind as it streams past, providing anywhere from 15 minutes to several hours of advance warning before storms reach our planet's magnetosphere. The art of space weather forecasting lies in interpreting these measurements and predicting their effects on Earth. Unlike terrestrial weather, with its visual cloud formations, space weather is largely invisible, revealing itself only through effects on magnetic fields and energetic particles. One of the most crucial measurements is the orientation of the magnetic field carried by solar storms. When a solar storm carries a magnetic field pointing southward, opposite to Earth's northward field, the two can connect efficiently, leading to strong geomagnetic activity and spectacular auroras. This magnetic field orientation can change unpredictably during a storm's journey from Sun to Earth, making precise forecasting challenging. A storm that initially appears likely to cause significant disruption might rotate its magnetic field orientation en route, arriving with much less impact than predicted. Solar observatories add another monitoring layer, watching the Sun's surface for magnetic eruptions, while advanced computer models attempt to predict when and where eruptions might occur. Yet space weather forecasting remains as much art as science, requiring experienced forecasters who can interpret subtle patterns in data streams and recognize the signs that precede major events. The human element becomes particularly important during rapidly evolving situations, when experienced forecasters can spot patterns that complement the mathematical predictions of sophisticated computer models. The consequences of accurate space weather forecasting extend far beyond academic curiosity. Power companies prepare for geomagnetically induced currents that might threaten electrical grids. Airlines modify flight routes during radiation storms, and satellite operators place spacecraft in protective modes when major storms are predicted. The International Space Station adjusts operations during severe space weather events, sometimes delaying spacewalks or moving astronauts to more shielded areas. Perhaps most remarkably, space weather forecasting has evolved from scientific curiosity to operational necessity in just a few decades, paralleling our civilization's growing dependence on space-based technology. As we continue to expand our presence in space and rely increasingly on satellite-based systems, the gentle art of watching the invisible sky becomes ever more crucial to maintaining the technological infrastructure that supports modern life. In the quiet hours before dawn, space weather forecasters around the world monitor streams of data flowing from their cosmic observatories, practicing a form of scientific meditation, watching, waiting, and interpreting the subtle signs that reveal the sun's intentions, preparing to warn the world when the next cosmic storm begins its journey across the void toward our magnetically protected planet.